There is a silence older than silence itself. Imagine a darkness so complete that even the word darkness feels inadequate. A void without measure, without scale, without even the rhythm of ticking seconds to mark its stillness. This is not the quiet of a cavern or the emptiness between stars. It is something more profound, the absence of time itself. And yet, out of this unfathomable stillness, the universe we know erupted in an instant of unimaginable brilliance, the Big Bang. That singular moment, when space unfurled and time began to tick, is often described as the ultimate beginning. But was it? Or could there have been something, anything, before the first second? To ask what happened before the Big Bang is to step beyond the comfortable ground of science and into a borderland where physics and philosophy intertwine. It is to challenge our intuition about beginnings and endings and to confront the possibility that the birth of our universe may not have been the birth of everything. For generations, cosmologists, philosophers, and dreamers alike have gazed into this abyss, daring to imagine what might lie beyond our cosmic origin story. The Big Bang Theory, as we know it, is not so much a theory of creation as it is a theory of evolution. It describes how the universe expanded from a hot, dense state some 13.8 billion years ago, cooling, condensing, and giving rise to stars, galaxies, and planets. It is a triumph of modern science, supported by the faint afterglow of radiation that still permeates the cosmos, the cosmic microwave background, and the ever-expanding fabric of space itself. But it does not tell us what ignited this expansion, nor whether there was something before. It is as if we have walked into a theater to watch a grand performance, but the curtain rises on the second act, leaving us to wonder what came before. The question of before is not trivial. Time, as Einstein revealed, is not an independent backdrop, but part of the fabric of space-time itself. If time began with the Big Bang, then perhaps the question is meaningless. Perhaps there was no before, no ticking clock, no stage upon which events could unfold. Yet the human mind resists such boundaries. We instinctively search for causes behind effects, for stories behind origins, and so the pursuit of what preceded time itself becomes an irresistible quest. Over the past century, theories have proliferated, each more daring than the last. Some physicists suggest that our universe is just one bubble in an eternal cosmic foam, where Big Bangs blossom endlessly, each giving birth to its own domain of space and time. Others imagine a universe that contracts and expands in an infinite cycle, each Big Bang merely the rebirth of a cosmos that has died before. Still others speculate about quantum fields, where fluctuations in a primordial nothingness could spark universes into being like sparks flying from a fire. None of these ideas are proven. All of them dance at the edge of what we can know. And yet they offer tantalizing visions of a reality larger and stranger than we ever dared to imagine. The story begins, as so many scientific revolutions do, with simple curiosity. In the early 20th century, astronomers like Edwin Hubble discovered that the galaxies are rushing away from us, carried outward by the swelling expansion of space. Reverse the film reel and everything converges. Stars, galaxies, and atoms themselves compressing into a single point of infinite density, a singularity. For decades, cosmologists accepted this as the ultimate boundary, the Big Bang as the true beginning. But singularities are places where our equations break, where the known laws of physics collapse into nonsense. They are less a final answer than a signal that our understanding is incomplete. In the 1960s and 70s, as the seeds of modern cosmology matured, thinkers like Hawking and Penrose showed that singularities are not just mathematical oddities, but inevitable consequences of general relativity. If our universe is expanding now, it must have sprung from a singularity in the past. Yet Hawking, always restless, began to wonder whether quantum mechanics, the strange probabilistic language of the very small, could soften that singularity, replacing the idea of a sharp beginning with something more subtle. Could quantum physics blur the edges of time itself, transforming the notion of a first moment into something more fluid? This line of thought gave rise to some of the most audacious ideas in modern physics. Perhaps time, instead of being a straight line with a fixed starting point, is more like the surface of the Earth, finite but without edges. Walk far enough south, you reach the South Pole. Beyond that, there is no further south. In this view, the Big Bang might not have been the beginning of time, but rather a kind of boundary, like the pole, beyond which before simply loses its meaning. It is a breathtakingly elegant idea, but one that leaves us uneasy, as though it hides more than it reveals. As technology advanced, so too did our capacity to probe these mysteries. The cosmic microwave background, discovered accidentally in 1965, became a kind of fossil record of the early universe, whispering to us from just 380,000 years after the Big Bang. With satellites like COBE, WAMAP, and Planck, scientists mapped this radiation with exquisite detail, uncovering tiny fluctuations that would one day grow into galaxies. Yet for all their precision, these maps stop short of the ultimate frontier. They do not pierce the veil of the first instant. They leave us staring at a wall of opacity, tantalized by what lies beyond. To push further back, physicists turn to the language of quantum theory and string theory, speculating about dimensions curled too tightly for us to see, and brains, vast, higher-dimensional sheets of reality that might collide to trigger Big Bangs. In these scenarios, what we call the beginning could be just the echo of a cosmic collision, a spark igniting from realms beyond our perception. The mathematics is breathtaking, the possibilities endless, but evidence remains elusive, and so the debate continues, fueled as much by imagination as by data. And yet, perhaps this is precisely the point. The search for what came before the Big Bang is less about arriving at a final answer than about expanding our vision of what reality could be. It forces us to confront the limitations of human knowledge, to accept that our universe may be but a single verse in a grander cosmic symphony. And if time had a different shape, if beginnings and endings are not what they seem, then our place in this story becomes all the more mysterious. The journey into this mystery has only just begun. To truly grasp how time itself could have emerged from something beyond time, we must travel deeper into the realms where quantum mechanics and gravity wrestle for dominance, where the very definition of reality is rewritten. It is here in this twilight zone between physics and metaphysics that we will search for answers. Answers that could redefine not just the universe, but the meaning of existence itself. To follow the trail of time back toward its possible origins, we must step into a realm where the everyday rules of reality no longer hold sway. At human scales, time feels steady, unwavering, a river that flows only forward. Our lives are pinned upon it like beads on a string, each moment giving way to the next in relentless succession. But as we descend toward the earliest fractions of the universe's existence, that river becomes turbulent, frothing, uncertain. It is here, within the smallest slices of time imaginable, that the seeds of cosmic creation may lie hidden. At the threshold of the Big Bang, we encounter what physicists call the Planck era, named after Max Planck, one of the founding fathers of quantum theory. This unimaginably brief epoch, just 10 to the negative 43 seconds after the supposed beginning, marks a boundary we cannot yet cross. Our laws of physics break down here because the two great pillars of modern science, Einstein's general relativity, which governs gravity and the grand architecture of the cosmos, and quantum mechanics, which rules the subatomic world, refuse to cooperate. Relativity describes a smooth, continuous fabric of space-time, while quantum theory demands granularity, uncertainty, and wild fluctuations. Both are correct in their domains, yet when pressed together at the dawn of time, they yield paradox. To truly know what happened before or at the Big Bang, we need a theory that unites them, a quantum theory of gravity. This search has consumed generations of scientists, inspiring some of the most daring ideas in modern thought. String theory, for instance, envisions the basic building blocks of reality not as point-like particles, but as vibrating strings of energy, tiny filaments whose harmonies give rise to the particles and forces we observe. According to string theory, there may be more dimensions than the four we experience. Extra dimensions, curled up too tightly to detect, might harbor the keys to understanding the birth of time itself. If true, then the Big Bang could have been not the beginning of everything, but a transformation, an event shaped by structures hidden in dimensions beyond our sight. An even more radical vision is that of the multiverse. Imagine an ocean without shore, stretching infinitely, upon which countless bubbles arise and drift, each bubble its own universe, with its own laws, constants, and histories. In this cosmic sea, our universe is but one bubble, born not from nothing, but from the frothing quantum energy of a greater whole. Here, the Big Bang is not unique, but common, an event repeated endlessly, scattering time and space like sparks from a fire. To some, this vision offers an answer to the riddle of fine-tuning, why the laws of our universe seem so precisely calibrated for life. If there are countless universes, then it is not surprising that in at least one, the conditions align to produce beings capable of asking such questions. But even as these grand theories capture imaginations, they remain speculative, perched on the edges of what science can verify. We are left with hints, with mathematical consistency, but without direct evidence. To move closer, scientists peer not only into equations, but into the heavens themselves, searching for faint imprints left upon the cosmos by events that may have preceded the Big Bang. One such imprint could lie in the polarization of the cosmic microwave background, the afterglow of the early universe. Patterns in this faint radiation might carry the signature of gravitational waves, ripples in space-time itself generated in the universe's first instance. If detected, these ripples could point us to the physics of the very beginning, perhaps even to a time before the Bang. In 2014, a team announced that they had found just such evidence, only for it to be revealed later as dust within our own galaxy masquerading as a cosmic signal. The disappointment was profound, but the search continues, relentless, because the stakes are so high. Beyond the scientific details lies something more elemental, the human hunger to know. Since ancient times, civilizations have grappled with the question of origins. In myths and sacred texts, creation emerges from chaos, from primordial waters, from the will of gods. These stories, though framed in spiritual language, share an echo with our modern search. They too attempt to reach beyond the veil of time, to imagine a before. Now, with the tools of physics, mathematics, and telescopes that reach to the edge of the observable universe, we continue that same quest, though armed with a different language of truth. Stephen Hawking himself offered one of the boldest interpretations of what might have come before. In his no-boundary proposal, developed with James Hartle, he argued that the concept of time before the Big Bang may be meaningless. In their model, the universe has no sharp beginning. Instead, time behaves like a spatial dimension near the origin, curving smoothly like the surface of a sphere. Just as the Earth has no edge where the surface abruptly ends, the universe, they suggested, has no singular point of before. Time emerges gradually, like dawn breaking over the horizon, and asking what happened before the Big Bang is as meaningless as asking what lies south of the South Pole. It is an answer that is at once profound and unsettling. The beginning of time may not be a boundary, but a transition. But other cosmologists challenge this view. They argue for models in which the Big Bang is not the beginning, but a bounce. In these scenarios, the universe did not emerge from nothing, but from a prior phase of contraction. As space shrank, densities soared until quantum effects reversed the collapse, igniting a new era of expansion. This big bounce replaces creation with cycles, universes collapsing, bouncing, and expanding in a rhythm without end. In this picture, time stretches infinitely in both directions, with no absolute beginning, only transformations. Such a cosmos is less like a story with a first page and more like a melody looping endlessly, variations upon a theme. The implications of these ideas are staggering. If the universe has no absolute beginning, then perhaps time itself is eternal. But if time had to be born, then there once was a state beyond time, a realm without before or after. To conceive of such a condition is nearly impossible, for our minds are wired to think in sequences. Yet physics may demand it. In certain quantum cosmology models, the pre-Big Bang universe exists in a timeless state, a static field of possibilities, until a quantum fluctuation, random, spontaneous, crystallizes into a universe where time begins to tick. In this way, reality may have emerged from a timeless sea, not unlike the myths of old, though described now in the stark language of physics. Still, none of this answers the ultimate question, why is there something rather than nothing? Even if the Big Bang arose from a quantum fluctuation, why was there a field to fluctuate in? Even if our universe is one bubble among many, why does the sea exist? These are questions that perhaps no scientific theory can resolve fully, questions that bleed into philosophy and metaphysics. Yet the pursuit itself reshapes our understanding, reminding us that the cosmos is deeper, stranger, and more mysterious than we could ever imagine. As we continue this journey, the story only grows richer. With each new theory, each new discovery, the picture of the universe's possible beginnings becomes more intricate. And yet, as we trace these threads, we also circle back toward ourselves, for hidden in this quest for cosmic origins is a reflection of our own longing to know where we came from, to anchor ourselves in a story larger than our brief lives. What came before the Big Bang may never be fully knowable, but the very act of asking reshapes how we see the universe and our place within it. And so we venture further into the realms of entropy and time's arrow, into the mysteries of black holes, into the very nature of reality itself. For to understand how time could have begun, we must also understand how it flows and why it moves only one way. If we are to grasp how time itself may have begun, we must confront a profound puzzle. Why does time seem to have a direction? Why does it flow from past to future, never in reverse? In the equations of physics, the laws of motion work just as well backward as forward. The mathematics does not privilege one direction over the other. And yet, in our experience, the difference between past and future is unmistakable. We remember yesterday, but not tomorrow. We grow older, not younger. Broken glasses do not leap back together, and stars do not unburn their fuel. Something enforces this one-way flow. That something is entropy. Entropy is the measure of disorder, of the number of ways a system can arrange itself. A neat stack of cards has low entropy. A shuffled deck has high entropy. In everyday life, entropy tends to increase. Heat spreads, structures decay, and order gives way to chaos. This relentless tendency underpins the arrow of time. The future is simply the direction in which entropy increases. But here lies the great enigma. If entropy increases with time, then the past must have begun in a state of extraordinarily low entropy. The early universe, just after the Big Bang, was hot, dense, and remarkably uniform, smooth, featureless, almost too perfect. And this smoothness is itself highly improbable. Why should the universe have started in such an exquisitely ordered state? Why not a messy, high-entropy chaos from the start? This question is not just about physics, it is about the very possibility of time as we know it. The physicist, Roger Penrose, has emphasized this puzzle for decades. In his view, the low-entropy beginning of the universe is not something we can take for granted. It cries out for explanation. Without it, the arrow of time would not exist. Without it, the unfolding of history, from galaxies to life to human thought, would not be possible. Time itself, in its flowing, irreversible sense, is built upon the bedrock of this improbable beginning. And so the mystery of what came before the Big Bang is intertwined with the mystery of entropy. Some have suggested that inflation, the brief explosive expansion of the universe in its earliest moments, might offer a clue. Proposed by Alan Guth in the 1980s, inflation posits that a tiny fraction of a second after the Big Bang, the universe ballooned outward at an extraordinary rate, smoothing and flattening its structure. This could explain why the cosmos looks so uniform today. But inflation itself requires conditions to begin, and it does not fully resolve the entropy problem. If anything, it pushes the mystery further back. Why were the conditions right for inflation in the first place? Penrose, ever bold, has put forward his own radical idea, conformal cyclic cosmology. In this vision, the universe is not a single story, but an endless sequence of eons. Each eon begins with a Big Bang and ends in a vast empty expanse where all matter decays, black holes evaporate, and only radiation remains. At that point, entropy has reached its maximum, and yet, strangely, it can also be considered low again, because without mass, without clocks, without change, the concept of entropy loses meaning. The end of one universe in this way becomes indistinguishable from the smooth beginning of the next. The arrow of time resets, and a new eon is born. If this is true, then our universe may carry echoes of a time before the Big Bang, not a bounce, but a transformation, the passing of a torch from one cosmic era to another. Penrose has even suggested that certain patterns in the cosmic microwave background might be the fingerprints of black holes that died in a previous eon. The evidence is debated, controversial, but the idea is haunting, that our universe is just one link in an infinite chain of cycles, each erasing its predecessor, and yet whispering traces of what came before. Other physicists approach the problem from the quantum side. If the universe began as a quantum fluctuation, then perhaps entropy is not something imposed from outside, but something emergent, a property that crystallizes as the cosmos unfolds. In certain models of quantum cosmology, time itself is not fundamental, but arises from correlations between quantum states. In such a picture, the arrow of time may not have been born at the Big Bang, but could have emerged gradually as complexity built and the universe settled into its expansion. And then there are black holes, the most enigmatic objects in the cosmos, and perhaps the key to unlocking the connection between entropy and time. According to the work of Jacob Bekenstein and Stephen Hawking, black holes are not just gravitational traps, but thermodynamic objects. They possess entropy, encoded in the area of their event horizons. This insight was revolutionary. It suggested that the ultimate disorder of the universe might be written on the surfaces of these cosmic abysses. If entropy and information are linked at such a fundamental level, then perhaps the entire universe is itself a kind of hologram, with time and space emerging from deeper, more abstract principles. The holographic principle, championed by Gerard Tooft and Leonard Susskind, takes this to its extreme. It proposes that all the information in our three-dimensional universe may be encoded on a two-dimensional boundary, much as a hologram contains a 3D image in a flat sheet. If true, then time itself could be a projection, not a fundamental reality, but an emergent property of information unfolding. In this view, asking what came before the Big Bang might be like asking what happened before a film begins. The story exists, but time itself is a construct of the projection. These ideas challenge our deepest intuitions. They remind us that time may not be the universal clock we assume, but a fragile thing, born of conditions that themselves cry out for explanation. The universe's arrow of time depends on its improbable low-entropy birth. To know how time could have begun, we must understand why that beginning was so ordered. Was it chance, a necessity of deeper laws we have yet to uncover, or the inheritance of a cycle that repeats beyond our grasp? Even as we wrestle with these abstractions, we are reminded of their consequences. Without an arrow of time, there is no memory, no history, no evolution. The story of the cosmos and of us is written in the ink of entropy. Stars burn because time has a direction. Life evolves because disorder increases. Consciousness itself, built from neurons firing in sequence, depends on the relentless push of time's arrow. The beginning of time is not only a question of physics, it is the foundation of existence. Yet the arrow of time leads to a final reckoning. For if entropy always increases, then one day it will reach its maximum. The universe will cool, expand, and fade into what is called the heat death, a state of endless, featureless equilibrium, where nothing changes, nothing happens, and time itself becomes meaningless. Just as the arrow of time was born at the universe's beginning, so it will die at its end. Between those two bookends lies everything we have ever known. And so the search for what came before the Big Bang is inseparable from the search for what lies at the end. For in that symmetry between origin and destiny may lie the deeper truth of time itself. If cycles exist, then the end may seed a new beginning. If time emerged once, perhaps it will emerge again. The story of before is also the story of after, bound together in a cosmic symmetry we have only begun to glimpse. To chase this symmetry further, we must journey into the hearts of black holes, those enigmatic engines where space and time are twisted to their limits. For it may be there, in the shadow of their event horizons, that the secret of time's beginning is hidden. To understand how time itself may have been born, we must descend into the darkest corners of the cosmos, where gravity grows so fierce that even light cannot escape. Black holes are not merely exotic byproducts of stellar death. They are laboratories at the limits of space and time. In their depths, the laws of physics converge and clash, forcing us to confront questions as ancient as the universe itself. It is here, in these cosmic abysses, that the secret of what came before the Big Bang may hide. A black hole forms when a massive star exhausts its nuclear fuel. Without the outward push of fusion, gravity takes command, crushing the star into a point of nearly infinite density, a singularity. Around this singularity, space itself is bent so dramatically that a boundary forms, the event horizon. Once crossed, no signal, no particle, no beam of light can return. From afar, a black hole appears eternal, a dark sphere suspended in space. But inside, all paths lead inward, to a place where time itself is drawn to a halt. At least, that is what classical relativity tells us. Yet, in the 1970s, a profound discovery revealed that black holes are not the eternal prisons they seemed. Stephen Hawking showed that quantum effects at the event horizon cause black holes to emit faint radiation. Over immense timescales, they evaporate, shrinking, and ultimately vanishing. This insight united thermodynamics, quantum theory, and gravity in a way no one expected. Black holes, it turned out, possess entropy, their measure of disorder proportional not to their volume, but to the area of their surface. This was no small detail. It suggested that the universe may store its information not in three-dimensional space, but on two-dimensional boundaries. This realization laid the foundation for the holographic principle, which proposes that all of reality could be described by data inscribed on a surface. If this is true, then our universe itself may be a projection, a kind of cosmic hologram. And if that is so, then perhaps time, the flow we feel so deeply, is not fundamental but emergent. It might rise from the organization of information, just as warmth emerges from the dance of countless molecules. This idea reshapes how we think about the Big Bang. If time emerges from information, then the beginning of time is not a singular moment of creation, but the birth of structure, of order that allows entropy to increase. Before the Big Bang, there may have been a state of perfect symmetry, a timeless sea where no information distinguished one moment from the next. The Bang would then mark not the origin of existence, but the breaking of symmetry, the first distinction, the moment when the cosmic ledger began to record. The connection between black holes and the origin of time grows deeper when we consider what happens to information. If black holes evaporate, does the information about what fell inside vanish with them? For decades, this was a central paradox. Hawking radiation appeared random, carrying no imprint of what formed the black hole. If true, this would mean that information, one of the fundamental currencies of physics, could be lost. But in quantum mechanics, information cannot be destroyed. The clash between these principles revealed a crack in our understanding, one that might reach back to the very birth of the universe. Many now believe that the paradox is resolved. Information is not lost, but somehow encoded in the radiation itself, scrambled beyond recognition, but preserved. If true, this means that black holes do not erase history, but transform it. The ultimate collapse becomes a seed of new order. Could the universe itself be a kind of black hole? Could the Big Bang be seen as the flip side of a black hole's death, an explosion of information released into a new domain of time? Some theorists have dared to suggest exactly that. In certain models, what we perceive as the Big Bang may be the white hole counterpart of a black hole, the other side of a cosmic tunnel, where matter and energy crushed in one universe erupt into another. If such a process is real, then time in our cosmos could be born from the death throes of another, a grand recycling in which every collapse is also a creation. These speculations tie into broader visions of a multiverse. If each black hole births a new universe, then our cosmos could be one of countless offspring, its physical laws determined by the conditions of its parent. In this picture, universes reproduce, evolve, and branch like a cosmic family tree. Time itself becomes a lineage, stretching across generations of universes. The Big Bang was not a beginning, but a continuation, a pulse in an eternal heartbeat. The elegance of these ideas is only matched by their audacity. Evidence is scarce, but black holes give us a window. By studying their radiation, their mergers, and the gravitational waves they unleash, we may glimpse hints of the deeper structure of reality. Already, detectors like LIGO and Virgo have opened a new era of astronomy, catching the ripples from colliding black holes billions of light-years away. Each detection brings us closer to probing the fabric of space-time itself, and perhaps, in time, closer to answering what happened before time began. Yet even as we look outward, the implications turn inward to the deepest questions of meaning. If black holes preserve information, then nothing is ever truly lost. Every particle, every event, every whisper of history is written into the fabric of the cosmos. If the universe itself was born in such a process, then perhaps our very existence is the echo of information carried across from before the bang. The atoms of our bodies may be inscribed with a memory older than time, though it is written in a language we have yet to decipher. Still, mysteries remain. If the universe is a hologram, where is the surface upon which it is inscribed? If time is emergent, what lies beneath it? Is there a deeper reality, timeless and formless, from which our ordered world arises? Or are these questions themselves misguided, artifacts of our human perspective, straining to impose causality where none exists? These are not easy questions. They demand humility, reminding us that our greatest theories are but lanterns in the fog, lighting only a few steps ahead. Beyond lies a darkness as deep as any black hole, filled with possibilities we can scarcely imagine. And yet it is in chasing this darkness that we expand the boundaries of the known. The link between black holes and the Big Bang is not merely a curiosity of theory. It forces us to confront the possibility that time itself is not linear but cyclical, not absolute but emergent. It suggests that the question of before is not nonsense, but a doorway into a greater understanding, that the universe's beginning may be tied to its end, and that both are written into the same fabric of entropy, information, and gravity. From the event horizons of black holes to the first horizon of time, the story is the same. Information persists, structure emerges, and from the depths of collapse, new beginnings arise. In the shadows of these cosmic giants, we glimpse the faint outline of a truth too vast for us yet to hold. A truth that the birth of time may not have been the first note in the cosmic symphony, but merely the latest refrain. But if the Big Bang was not the beginning, then where does the story lead? To trace it further, we must venture into the quantum fabric itself, where particles blink in and out of existence, and where the very act of observation gives rise to reality. It is in this quantum haze that the ultimate seeds of time may be planted, waiting to burst forth into universes like ours. To trace time back to its origins, we must leave behind the colossal gravities of black holes and plunge into the opposite extreme, the quantum realm, where particles flicker in and out of existence, where uncertainty reigns, and where nothingness itself seethes with hidden energy. It is here, in this trembling vacuum, that many physicists believe the first whispers of time were born. For if the Big Bang was not the true beginning, then perhaps it was the awakening of structure from a quantum ocean older than time itself. The word vacuum suggests emptiness, a void devoid of matter and energy. Yet in the quantum view, emptiness is never truly empty. Even in the darkest void, fields permeate space, restless and vibrant. According to quantum field theory, every kind of particle is an excitation of an underlying field that stretches across the cosmos. The electron has its field, the photon its own, and so too for quarks, gluons, neutrinos. The vacuum is the ground state of these fields, not stillness, but a sea of fluctuations, like the surface of an ocean in constant motion. These fluctuations are not hypothetical. They can be measured. In laboratories, they produce observable effects such as the Casimir force, a delicate attraction between metal plates caused purely by the restless jitter of the vacuum. At cosmic scales, they leave fingerprints in the distribution of galaxies, subtle variations seeded by quantum fluctuations that were stretched across the sky during the universe's earliest moments. The patterns we see today in the clustering of stars are echoes of quantum noise, magnified to cosmic grandeur. If the vacuum is this fertile, then perhaps it is not surprising that an entire universe could spring from it. Some physicists, including Edward Tryon in the 1970s, proposed that the Big Bang was a quantum fluctuation, a moment when the vacuum gave birth to a bubble of space-time. Normally, such fluctuations vanish in an instant, like bubbles popping back into the sea. But if conditions are right, one bubble may inflate, growing instead of collapsing. In this way, a quantum fluctuation could blossom into a universe with its own time, space, and history. This idea is seductive in its simplicity, a universe from nothing. But of course, nothing here is not truly nothing. It is a seething quantum field, a substrate with rules and properties. Where did that come from? What is the origin of the vacuum itself? Once again, the question recedes, like a horizon that draws away as we approach. Still, the possibility that our cosmos emerged from a quantum sea suggests that the birth of time is not an absolute beginning, but a transition, a phase change in the fabric of reality. One of the most powerful tools for describing this transition is inflationary theory. During inflation, space expanded at an exponential rate, doubling again and again in a fraction of a second. Quantum fluctuations, normally confined to the tiniest scales, were blown up to cosmic size, leaving imprints that would one day seed galaxies. Inflation explains why the universe is so smooth and flat on large scales, and why it looks the same in every direction. It is one of the most successful theories of modern cosmology. Yet inflation itself raises deeper mysteries. To occur, it requires a peculiar form of energy, embedded in a scalar field often called the inflaton. Where did this field come from? Why did it exist at all? And why did it eventually decay, ending inflation and filling the universe with the hot plasma of the Big Bang? Inflation solves problems, but it also creates new ones, pushing the question of origins into unfamiliar terrain. Some versions of inflation predict that it never truly ends, that while inflation ceases in some regions, it continues in others. This leads to eternal inflation, a process in which countless bubble universes are born within an ever-expanding background. Our universe would then be just one bubble in an endless foam, each with its own beginning of time, each seeded by quantum fluctuations. Here, the notion of before becomes slippery. In eternal inflation, there may be no singular beginning, but rather a fractal-like process, stretching backward indefinitely, birthing universes without end. Time itself may be embedded within this vast structure, with no ultimate origin. Or perhaps time in the multiverse is different, more complex, not the single arrow we experience, but a branching web of beginnings. Still, quantum theory tempts us with an even stranger possibility, that time itself is not fundamental, but emergent. In the equations of quantum cosmology, there are models in which time does not exist at the most basic level. The universe is described by a wave function that contains all possible configurations of space and matter, timeless and eternal. What we experience as the flow of time emerges from correlations within this wave function, much as the concept of temperature emerges from the jostling of countless molecules. In this view, asking what came before the Big Bang may be like asking what came before the melting of ice. There was no before, only a different state of the system. Some of these models propose that the universe before the Big Bang existed in a quantum timeless state, a superposition of all possible beginnings. The Big Bang was not a singular explosion, but a quantum transition, a crystallization of one reality from a haze of possibilities. This perspective echoes the way particles behave in the laboratory, existing in multiple states until measured, at which point they choose. The cosmos, then, may have been a wave function waiting to collapse into the time-bound reality we inhabit. This idea is not merely poetic, it is grounded in attempts to reconcile general relativity with quantum mechanics. In approaches like loop quantum gravity, space-time itself is quantized, built from discrete loops woven together. In these theories, the singularity of the Big Bang dissolves into a bounce, where a prior universe contracted and rebounded, avoiding infinite densities. At the bounce point, time as we know it may vanish, replaced by a quantum geometry where before and after lose meaning. The Big Bang becomes a door between eras, not a beginning, but a bridge. And yet we are left with a sense of vertigo. If time is emergent, if the universe is born from fluctuations in a timeless sea, then our basic intuitions falter. What does it mean for something to exist outside time? How can a process occur in a realm without before or after? Perhaps these are the wrong questions, shaped by the limitations of human thought. Just as Newtonian physics gave way to relativity, perhaps our very concept of time must evolve, replaced by something stranger, deeper, beyond our current grasp. In the meantime, experiments inch us forward. Quantum fields are probed by particle accelerators. Satellites scan the cosmic microwave background, hunting for imprints of inflation. Quantum theorists wrestle with equations that describe the universe as a wave function. Piece by piece, the fog may lift, or perhaps it will only grow denser, revealing not answers, but new mysteries, each more wondrous than the last. For now we can only stand in awe. From black holes to quantum fields, from entropy to timeless wave functions, the story of time's birth is woven from threads both fragile and grand. And as we follow these threads, we are reminded that the universe may be far larger, far stranger than our imaginations can hold. Time itself, the river in which our lives flow, may be but a ripple in a greater ocean, one that stretches beyond beginnings and ends. And if so, then the Big Bang was not the start of everything, but the beginning of our chapter in an infinite story. To explore what lies beyond, we must not only expand our science, but also our sense of wonder. For the greatest truths of time may not be measured in equations alone, but in the way they reshape our understanding of existence. But if quantum fluctuations gave birth to our universe, then one question remains. What determines the laws that govern it? Why these particles, these forces, this unfolding of time, and not another? To approach this mystery, we must step beyond physics into the realm of cosmic fine-tuning, where the very fabric of reality seems designed with uncanny precision. The deeper we chase the question of how time began, the more the universe answers us with another puzzle. Why does it work this way at all? Why does it have these laws, these particles, these precise conditions that allow for galaxies, stars, planets, and ultimately life? The mystery of origins is not only about what came before the Big Bang, but also why the Bang itself was so delicately tuned. For in the chaos of possibilities, our universe seems improbably suited for existence. Consider gravity, that most familiar of forces. If its strength were even slightly different, the cosmos would be unrecognizable. Stronger gravity and stars would burn too quickly, collapsing into black holes before life had a chance to arise. Weaker gravity and matter would never have coalesced at all. No stars, no planets, just an endless thin fog of particles. Or think of the electromagnetic force. Shift its strength by a fraction, and chemistry as we know it would collapse, atoms refusing to bond, molecules failing to form. Even the masses of particles, the proton, neutron, electron, are balanced with eerie precision. A slight imbalance in the nuclei that form the heart of atoms would never have emerged. These are not minor details, they are the foundations of existence. The cosmos seems poised on a knife's edge where the slightest deviation would render it sterile. Physicists call this the problem of fine-tuning, and it raises a profound question: why? Why does the universe have just the right conditions for time to flow, for complexity to build, for consciousness to awaken? Was this an accident, a stroke of blind luck in a sea of possibilities? Or is there something deeper, something inevitable about the laws we see? One response is the anthropic principle, the idea that we can only observe a universe compatible with our existence. In other words, it is not surprising that the universe is fine-tuned for life, because if it were not, we would not be here to notice. This explanation, while logically sound, feels unsatisfactory, like a magician's flourish that distracts without revealing the trick. To many, it seems to sidestep the deeper mystery rather than resolve it. Another possibility is that our universe is not alone. If there are countless universes, each with different laws, constants, and properties, then fine-tuning may not be surprising at all. We exist in one of the rare universes where the conditions allow life. Just as countless barren planets exist in our galaxy, but a few harbor life, so too might countless universes exist, but only a few allow observers. This vision is the multiverse, a vast landscape where every possibility plays out somewhere. The multiverse takes many forms. Eternal inflation creates bubble universes, each budding off from the inflating background, each with its own physics. String theory adds another layer, suggesting that hidden dimensions and vibrating strings allow for a vast number of possible configurations, perhaps as many as 10 to the 500 different universes. Within such immensity, the existence of at least one life-friendly cosmos becomes less astonishing. But even if the multiverse solves the riddle of fine-tuning, it raises a new question. What gave rise to the multiverse itself? Is it eternal? Did it too have a beginning? And what does it mean for time if, beyond our universe, there are other timelines unfolding, perhaps even with different arrows of time? Some physicists imagine that time itself might take on different characters in different universes. In some, it might flow as ours does, with entropy increasing, with histories unfolding. In others, time might be cyclical, looping endlessly. In still others, time might not exist at all, with reality frozen in a static configuration beyond our comprehension. If the multiverse is real, then our experience of time may be but one local manifestation, a parochial feature of our bubble, not a universal truth. This line of thought forces us to confront an uncomfortable possibility that our universe is not privileged, not central, but just one among an infinite variety. It diminishes the notion of a singular cosmic story and replaces it with an infinite library, each book telling its own tale, each bound by its own rules. And yet there is also a strange comfort in this vision. If universes are endless, then time too may be endless, reborn in every bubble, in every fluctuation. Our Big Bang becomes one act in a theater of infinite stages. But there are those who resist this vision, who argue that the multiverse, while seductive, is unfalsifiable, a hypothesis beyond the reach of experiment. Without evidence, they argue, it belongs more to philosophy than to science. They seek instead explanations within the boundaries of our own universe, searching for deeper laws that necessitate the conditions we observe. Perhaps the constants of nature are not accidents at all, but inevitable consequences of mathematics we do not yet understand. In this view, fine-tuning is not a mystery, but a reflection of deeper symmetries waiting to be revealed. Yet the tension remains. The beginning of time is entangled with the conditions of its unfolding. If the universe is fine-tuned, then its tuning is part of its origin story. To explain why time began is also to explain why it began in a way that allowed it to flow toward complexity, toward galaxies and stars, toward us. The stakes are more than academic. They touch on the ultimate question of why there is something rather than nothing. History reminds us how dangerous it is to assume finality. Once, humanity believed the Earth to be the center of the cosmos, the heavens revolving around us. That illusion shattered, replaced by the vision of a vast galaxy, and then of galaxies without number. Now, perhaps, we stand on the edge of another revelation, that even our universe is not unique, but part of something larger, stranger, more infinite than we can imagine. If so, then the beginning of time may not be the beginning at all, but only a local dawn in an eternal landscape of dawns. Still, the multiverse, even if true, does not erase the mystery. For even if there are infinite universes, why does the multiverse exist? Why are there laws at all, laws that govern inflating fields, vibrating strings, quantum fluctuations? The question of why something exists rather than nothing presses on, undiminished. We may circle it endlessly, like travelers orbiting a black hole, never reaching the singular heart of the mystery. And yet in the circling we learn. We glimpse the outlines of truths that reshape our place in the cosmos. To ask about time before the Big Bang is to stretch human thought to its limits, to challenge assumptions embedded in language and logic. It is to recognize that beginnings and endings may not be absolute, but contextual, shaped by the frameworks in which we view them. The search for origins is also the search for meaning. If the universe is fine-tuned, is it tuned for us? If time had a beginning, is it a creation or a necessity? If the cosmos is infinite, do we matter less or do we matter more as the rare consciousness able to ponder it? These questions cannot be separated from the science. They live within it, shadows cast by the light of discovery. And so the journey continues. To understand how time began, we must consider not only fields and forces, but the possibility that reality itself is a tapestry woven from deeper principles that may reveal themselves in patterns of the cosmic microwave background, in the collisions of black holes, in the dance of particles within accelerators. Principles that may tell us not only how time began, but why it flows and what awaits at its end. For the arrow of time, though relentless, may not be eternal. If entropy increases, if the cosmos drifts toward heat death, then the story may end in silence. But if cycles exist, or if universes bud endlessly, then every ending is a beginning, and time is reborn again and again. To explore this possibility, we must turn next to the ultimate fate of the cosmos, and the symmetry it may hold with its birth. If the story of time begins in mystery, it ends no less so. To understand the birth of time, we must also confront its death, the ultimate fate of the cosmos. For the way time concludes may reflect how it began: birth and death, expansion and collapse, order and disorder. These are not merely stages of the universe's history, but perhaps reflections of a deeper symmetry, a rhythm etched into reality itself. Our universe is expanding, carried outward by the momentum of the Big Bang. For decades, astronomers debated whether this expansion would last forever, or whether gravity, the great sculptor, would eventually halt and reverse it. The possibilities fell into neat categories. If the cosmos lacked enough matter, expansion would continue forever, slowing but never stopping, leaving the universe cold and diffuse. If enough matter filled space, gravity would one day overcome expansion, pulling everything back into a fiery big crunch. Each path seemed logical, grounded in the balance of forces. But the universe surprised us. In the 1990s, astronomers studying distant supernovae discovered that the expansion is not slowing, but accelerating. Some mysterious energy, dark energy, drives space apart, forcing galaxies away from one another with ever-increasing speed. Dark energy, which makes up nearly 70% of the universe, is perhaps the most profound enigma of modern cosmology. We do not know what it is, only that it dominates the fate of everything. If dark energy continues its work unchecked, the cosmos faces a chilling destiny: heat death. As galaxies recede beyond one another's horizons, their light will never reach us. Stars will burn out, one by one, their fuel exhausted. Black holes will evaporate into whispers of radiation. The universe will cool toward absolute zero, a vast, silent expanse where nothing stirs. Entropy will have reached its maximum, and time itself will lose meaning, for without change, there is no before or after. This vision is bleak, but it mirrors the puzzle of the beginning. Just as time's arrow emerged from a state of low entropy, so too will it dissolve when entropy reaches its peak. Time has a birth and a death, both defined by the structure of disorder. If the Big Bang was the spark that lit the arrow, then heat death is the darkness where the arrow fades. In this symmetry lies a haunting beauty. But some physicists see another possibility, that the end is not the end, but the beginning of a cycle. If the universe collapses in a big crunch, then perhaps that collapse rebounds, igniting a new expansion, a big bounce. In this view, time is not a line, but a loop, with no ultimate beginning or end. Every universe carries within it the seed of the next, entropy resetting with each cycle. The cyclical model has deep roots. Ancient cultures imagine time as a wheel, endlessly turning. Hindu cosmology speaks of kalpas, vast cycles of creation and destruction. The Stoics envisioned ekpyresis, a cosmic conflagration followed by rebirth. Modern physics, in its own language, echoes these visions. If the universe bounces, then our Big Bang was not the first, nor will it be the last. Time stretches infinitely in both directions, each eon following another in eternal rhythm. Roger Penrose's conformal cyclic cosmology, as we have seen, offers a different twist. Instead of a crunch and bounce, it envisions the end of the universe, when only radiation remains, as conformally equivalent to the smooth beginning of a new one. In this picture, the death of one cosmos flows seamlessly into the birth of another, without singularities, without boundaries. The arrow of time resets, not by reversal, but by transformation. The idea is speculative, but it offers an elegant link between the end and the beginning, weaving time into an infinite tapestry. There are even darker fates to consider. If dark energy grows stronger with time, accelerating expansion ever more violently, the universe could face a big rip. In this nightmare, galaxies are torn apart, then stars, then planets, then atoms themselves. Even the fabric of space-time would be shredded. Time would not drift into silence, but be ripped from existence in a cataclysmic finale. Yet even this horror holds echoes of creation. For in the destruction of all structure might new universes emerge. Could the Big Rip be the chaotic transition to another phase, another dawn of time? We do not know. But the symmetry between beginnings and endings continues to beckon, suggesting that the story of time is not linear but cyclical, not finite but eternal in form, if not in content. Philosophers, too, have long wrestled with this symmetry. Friedrich Nietzsche spoke of eternal recurrence, the endless return of the same events, looping forever. While his idea was metaphorical, physics gives it new weight. If cycles exist, then everything that happens may happen again in some form, across eons without number. The stars we see, the thoughts we think, the lives we live, could be echoes of countless pasts destined to repeat in countless futures. Yet cycles are not the only way to link the end and the beginning. Quantum cosmology suggests that in the heat death, when entropy is maximized, time itself may dissolve, leaving a timeless state akin to the one that preceded the Big Bang. In that timeless sea, quantum fluctuations may stir, birthing new universes, new arrows of time. The end, once again, becomes the womb of beginnings. The more we examine these possibilities, the more the boundary between origin and destiny blurs. The Big Bang and the ultimate fate are mirrors of one another, reflections across the vast expanse of cosmic time. To ask what came before the bang may be the same as asking what comes after the end. Both questions lead us into the same mystery, the nature of time itself. And so we are left with a paradox. Time seems both fragile and eternal, both bounded and unbounded. It begins in a low entropy state, and it ends in high entropy. Yet both ends are strangely alike, states where time itself may lose meaning. Between them lies everything: galaxies, stars, life, thought, history. Our existence is suspended between two abysses, one before and one after, each beyond our comprehension. This realization reshapes our place in the cosmos. We are not merely witnesses to a fleeting moment in an eternal void. We are creatures of time, born in its flow, destined to return to its silence. To understand how time began is also to understand who we are, beings whose entire existence depends on the improbable arrow drawn across the fabric of the universe. But the mystery deepens further still, for time is not only cosmic, it is also personal. Each of us carries within us a sense of time, a flow of memory and anticipation. Neuroscience tells us that our brains construct this sense from electrical patterns, from the firing of neurons. But why should the universe allow for such a phenomenon at all? Why should time, born from entropy and cosmology, become conscious within us? This question bridges the cosmic with the human, reminding us that the mystery of time is not only out there in galaxies and black holes, but also here, in the fragile theater of the mind. And so, to complete our exploration, we must turn inward. To understand time's origin, we must also ask why it feels as it does, why it shapes our thoughts and our lives. For the greatest mystery of all may not be what came before the Big Bang, but why the universe is such that time could awaken, could be felt, could give rise to meaning. Time is not only written into the fabric of the cosmos, it is inscribed into us. The mystery of its beginning is not just a question for physics, but a question for experience, for consciousness. We are not passive observers of time's river. We are creatures carried by its flow, aware of its passage, haunted by its limits. To understand how time began, we must also ask why it feels as it does, why the cosmos, born in fire and mystery, gives rise to beings who can sense the tick of seconds, remember the past, and imagine futures that do not yet exist. From the perspective of physics, time is a dimension, woven with space into a continuum. It does not flow in the equations. Past, present, and future coexist in what Einstein called the block universe. In this view, time is more like a landscape. Every moment exists, laid out in a four-dimensional tapestry. The flow we feel, the sense that now is distinct from then, is not fundamental but emergent. Yet for us, the flow is inescapable. we experience life as a succession, a march, a story unfolding frame by frame. Neuroscience offers clues. Our brains are machines of memory, stitching together fragments of sensory input into a coherent narrative. We do not perceive reality directly. We perceive a reconstruction, delayed by fractions of a second, filled in by expectation and memory. The sense of now is a construction, a moving window that stitches past to future. Without memory, there would be no time, only isolated instants, unconnected and meaningless. And without anticipation, there would be no future, only the weight of the present frozen in place. This suggests that time, as we live it, is as much psychological as physical. It is a marriage of entropy and memory, of cosmic order and neural circuitry. The arrow of time that began with the universe's low entropy finds its echo in the arrow of memory. We remember the past where entropy was lower, but not the future where entropy is higher. Our personal experience is aligned with the universe's thermodynamic direction. In this way, the grand and the intimate converge. And yet time in the mind is elastic. Moments of joy race past, moments of terror linger endlessly. Childhood summers stretch vast, while adult years compress into brevity. This elasticity is not mirrored in the cosmos. The universe ticks with impartial regularity. But perhaps this elasticity is another clue, that our consciousness is not merely riding time's flow, but participating in it, shaping it into meaning. The philosopher Augustine, writing 16 centuries ago, confessed his bewilderment. What then is time? If no one asks me, I know. If I wish to explain it to one that asketh, I know not. His words capture the paradox. Time is the most familiar thing, the medium of our lives, and yet it resists definition. Science has clarified some of its nature, but the lived experience remains mysterious. Why should matter, arranged in certain ways, become conscious of time at all? Some speculate that consciousness and time are deeply linked, that our sense of self, of continuity, arises from the very structure of temporal awareness. To be aware is to exist across moments, to stitch them together into identity. Without time, there may be no consciousness. Without consciousness, perhaps time itself loses its meaning. In this sense, the question of how time began is inseparable from the question of how awareness began. Both are emergent, both are relational, both arise from complexity. This connection takes us back to the origins of the cosmos. The Big Bang gave rise not only to space and matter, but to the conditions under which time could be felt. In a universe without structure, without order, time would be meaningless. But in a universe where stars form, where entropy increases, where memories can be encoded, time becomes something more than an abstract coordinate. It becomes a lived reality, culminating in beings who can wonder about its origin. And here lies a remarkable symmetry. The universe not only allows for time, but eventually produces creatures who can question it. We are time made self-aware, the cosmos reflecting upon its own unfolding. Our questions about the beginning of time are not external to the universe. They are the universe asking itself how it came to be. In this way, the mystery of before the Big Bang is both cosmic and intimate, both abstract and profoundly personal. But the story of time and consciousness also reveals its limits. Our minds evolved to navigate survival in a narrow window, to hunt, to flee, to love, to build. We are not equipped to imagine eternity, to grasp timeless states, to comprehend the infinitesimal fractions of a second at the universe's birth. Our sense of time may therefore be a distortion, a useful fiction imposed upon a reality that is far stranger than we perceive. To explore what came before the Big Bang, we must stretch thought beyond thought, imagination beyond experience. Quantum mechanics offers a parallel. In the quantum world, particles do not have definite positions or velocities until observed. They exist in probabilities, in superpositions, where past and future intertwine. Some physicists suggest that consciousness itself may be entwined with this process, that the act of observation, the awareness of time, plays a role in crystallizing reality. This idea remains controversial, yet it hints at a profound possibility, that the mystery of time cannot be separated from the mystery of mind. In this way, the birth of time may be as much about perception as about physics. Time may not be a universal, absolute entity, but a relational one, arising when systems interact, when complexity builds, when awareness arises. The Big Bang created the conditions for such interactions, but the full flowering of time, its felt reality, required the emergence of beings who could hold memories, who could anticipate futures, who could stand on a planet beneath the stars and ask, "What came before?" This realization humbles us, for it means that our search for cosmic origins is not detached but participatory. We are part of the very story we seek to understand, bound to it in ways we cannot escape. To ask about time before the Big Bang is to ask about the ground of our own existence, about why the universe is such that beings like us can exist at all. And yet, even as we reflect on the intimacy of time, the cosmic scale dwarfs us. The billions of years that stretch behind us, the trillions that may lie ahead, the incomprehensible expanse of galaxies, all of it renders human life fleeting, fragile. But perhaps this fragility is not cause for despair, but for wonder, that in so brief a span, in so small a corner of space, time has blossomed into consciousness. The poet William Blake once wrote, "To see a world in a grain of sand, and a heaven in a wildflower, hold infinity in the palm of your hand, and eternity in an hour." In our awareness of time, we already hold infinity. Every memory is a bridge to the past. Every dream is a glimpse of the future. Our finite lives, lived within the arrow of entropy, contain reflections of eternity. So, as we pursue the origins of time through physics and cosmology, we must also recognize that time is mirrored within us. Its beginning is not only out there in equations and singularities, but here, in the pulse of our hearts, in the rhythm of thought, in the fragile continuity of identity. To seek the beginning of time is to seek ourselves. And yet questions remain. If time is emergent, if it is a construction of physics and perception, then what lies beyond it? Can we imagine a state without time, a reality before beginnings? Or is such imagination forever closed to us, bound by the very flow we are trying to escape? To press this question further, we must venture back to the ultimate frontier, the singularity at the heart of the Big Bang, where space, time, and matter converge into paradox. To stand at the threshold of the Big Bang is to confront the singularity, the place where our equations falter, where the known laws of physics crumble into contradictions. In the standard model of cosmology, the universe, traced backward in time, shrinks to a point of infinite density, infinite temperature, infinite curvature of space. At that point, our mathematics produces nonsense, infinities that signal not reality, but the breakdown of our understanding. The singularity is less a place than a warning. Here, new physics must emerge. For decades, scientists treated the singularity as the ultimate beginning, the sharp edge of time beyond which no questions could reach. But as our understanding of quantum theory grew, it became clear that singularities are not so much answers as placeholders, gaps in knowledge demanding resolution. In black holes, as in the Big Bang, singularities signaled that we are pushing Einstein's general relativity beyond its domain. To move past them, we need a quantum theory of gravity, a framework that merges the continuous fabric of space-time with the discrete, probabilistic world of the quantum. Loop quantum gravity is one such attempt. It proposes that space-time itself is not smooth and continuous, but woven from tiny loops, like a fabric of threads at the smallest scales. In this theory, the singularity of the Big Bang dissolves. Instead of a point of infinite density, the universe contracts to a finite size, then bounces outward again. Time does not begin or end, but transitions, a cosmic heartbeat, pulsing through cycles of contraction and expansion. In this way, the singularity is replaced by continuity, and the question of before finds new meaning. There was a universe before ours, compressed, reshaped, and reborn in the bang we see as our beginning. String theory offers another vision. In its equations, particles are not point-like, but tiny vibrating strings, existing in higher dimensions curled up beyond perception. Singularities may be smoothed by these strings, their vibrations preventing the infinities of relativity. In some scenarios, our Big Bang was the result of a collision between higher dimensional membranes, or branes, floating in a grander space. When two branes collided, the energy released could ignite a new universe. In this picture, our cosmos is not isolated, but part of a larger multiverse, where brane collisions occur endlessly, each one birthing a new flow of time. The singularity, then, is not a wall, but a doorway, leading from one reality to another. And then there is the no-boundary proposal, offered by Stephen Hawking and James Hartle. In their model, the singularity evaporates entirely. The universe does not emerge from a point, but from a smooth, finite surface, where time gradually transforms from a spatial dimension into the temporal flow we know. Just as the Earth has no edge where it suddenly ends, the universe has no singular beginning, no sharp boundary to time. The Big Bang in this view is not a singular explosion, but a smooth transition, like the dawn emerging from the darkness. Asking what came before becomes meaningless, for time itself was not yet defined. These theories offer glimpses beyond the singularity, but none are proven. Each rests on mathematics, on elegance, on hints that may or may not be borne out by evidence. And yet they show us that the singularity need not be the end of inquiry. It is a horizon, yes, but horizons can be crossed. What makes the singularity so elusive is that it forces us to question the very nature of reality. If space-time is quantized, what does it mean to speak of continuity? If time emerges from correlations within a quantum wave function, what does it mean to speak of before and after? If the universe is one of many, what does it mean to call ours a beginning at all? Each question dissolves the familiar, leaving us adrift in abstractions that strain the limits of language. Yet singularities are not only theoretical curiosities, they have profound implications for the fate of information, of entropy, of time itself. If the Big Bang was a singularity, did it preserve information from a prior state, or was it a true reset, erasing all trace of what came before?
If black hole singularities preserve information through holography, might the Big Bang do the same? Could the structure of our universe carry faint imprints of a pre-bang reality, encoded in patterns we have yet to decipher? Physicists have searched for such imprints in the cosmic microwave background, the oldest light we can see. Some claim to find concentric circles or anomalies that could be echoes of collisions or cycles from before the bang. The evidence remains disputed, tantalizing but unconfirmed. Still, the search continues, for if such patterns are real, they would be the first fingerprints of time before time, the whispers of a story older than our universe. The singularity also confronts us with philosophical questions. If time began at the Big Bang, can we even ask what came before? Or is before a word without meaning in that context, like asking what lies north of the North Pole? If there was no time, then causality itself dissolves, for cause requires before, and effect requires after. In such a reality, the origin of the universe may not be an event, but a state, a condition without sequence. But perhaps this challenge is not a barrier, but an invitation. It may be that our deepest intuitions about time, about causality, about beginnings, are not fundamental truths, but approximations evolved to help us survive within a narrow band of reality. Just as Newton's mechanics gave way to relativity and quantum mechanics, so too may our concept of time give way to something stranger, deeper, more subtle. And so the singularity is not a dead end, but a frontier. It tells us that our current knowledge, as powerful as it is, remains incomplete. It beckons us to build new theories, to search for new evidence, to expand our imagination of what reality could be. It humbles us, reminding us that the beginning of time is not yet within our grasp, but perhaps one day will be. Yet even as we explore these possibilities, one truth endures. Whatever lies beyond the singularity, it gave rise to the universe we inhabit. From that mystery flowed galaxies, stars, planets, and life. From that unfathomable dawn arose consciousness, questions, wonder. The singularity may be inscrutable, but its consequences are written in the night sky, in the atoms of our bodies, in the ticking of every clock. And so we return to the paradox. The singularity is both nothing and everything, both the absence of explanation and the source of all things. To stare into it is to confront our ignorance, but also to glimpse the profoundest truth, that time itself may be a gift of transition, born from states we cannot yet imagine. To press further, we must not only seek the physics of singularities, but also the philosophy they demand. For the question of what came before the Big Bang is not only scientific, but metaphysical, bridging the boundary between what can be measured and what can only be imagined. In the next steps of our journey, we must explore these philosophical dimensions, where science meets wonder, and where the origin of time becomes inseparable from the question of meaning itself. Long before telescopes swept the skies and equations bent space-time, humanity pondered the mystery of beginnings. To ask what came before time is not a question unique to modern physics. It is an ancient riddle woven into myth, philosophy, and religion. Across cultures, stories of creation reach into the darkness before beginnings, searching for meaning in a place where words falter. In their own symbolic ways, these stories echo the very questions cosmologists wrestle with today. In Mesopotamia, one of the earliest civilizations, creation was imagined as order emerging from chaos. The primordial waters, personified as gods Apsu and Tiamat, clashed, and from their struggle, the heavens and the earth were formed. Here, before there was structure, there was a boundless sea, a formless state not unlike the quantum vacuum of modern physics. The act of creation was not from nothing, but from transformation, from chaos into cosmos. The Rig Veda, one of the oldest sacred texts of India, asks with haunting humility, who really knows and who can say whence it all came and how creation happened? It speaks of a time when there was neither existence nor non-existence, neither death nor immortality. The cosmos emerged not from a beginning, but from an undifferentiated state, mysterious and timeless. This resonates with contemporary ideas that time itself may be emergent, that the Big Bang was not a true beginning, but a transition from a state beyond our categories of thought. In ancient Greece, philosophers wrestled with the paradox of nothingness. Parmenides declared that nothing cannot be, and therefore the universe must be eternal. Plato spoke of time as the moving image of eternity, born when the heavens were fashioned. Aristotle saw time as dependent on motion, inseparable from change, and therefore eternal with the cosmos itself. The idea that time had a definite beginning troubled many thinkers. It seemed to violate reason itself. Later, Christian and Islamic philosophers embraced the notion of creation ex nihilo, creation from nothing. In this vision, time itself was created alongside the universe, born by divine will. Augustine, meditating on Genesis, concluded that time did not exist before creation. God created not only the heavens and the earth, but also time itself. So to ask what came was to misunderstand the nature of time. This perspective foreshadowed Hawking's no-boundary proposal by centuries, suggesting that before may be a meaningless concept when applied to the origin of time. Eastern traditions offered yet other visions. In Buddhism, the universe is cyclical, with countless world systems arising and passing away. Time is not linear, but circular, without ultimate beginning or end. This echoes the modern idea of a bouncing or cyclic cosmos, where big bangs and big crunches follow one another endlessly. Hindu cosmology likewise envisions cycles of creation and destruction, measured in kalpas, vast spans of time beyond human comprehension. In these traditions, the universe has no single birth, but an eternal rhythm, a cosmic heartbeat. These myths and philosophies, though framed in poetic or theological language, are not so distant from today's cosmological debates. They grapple with the same questions. Was there a beginning? Is time eternal? Can something emerge from nothing? What lies beyond the limits of thought? Science gives us new tools, but the questions are ancient, embedded in human curiosity from the start. The convergence of science and philosophy is nowhere more evident than in the confrontation with nothing. What does it mean for the universe to emerge from nothing? The physicist's nothing, a quantum vacuum seething with fluctuations, is not truly nothing at all. It has laws, structure, properties. Philosophers argue that even to describe nothing is to grant it existence. Absolute nothingness may be impossible to conceive, perhaps even impossible to exist. In this sense, the universe may not have emerged from nothing, but from something beyond our categories, a state that transcends the distinction. Modern philosophers of science debate whether the question of before the Big Bang is meaningful. Some argue it is a pseudo-question, like asking, what is north of the North Pole? Others insist it is legitimate, that there must be an explanation, even if hidden. The tension between these views reflects a deeper truth. Our concepts, forged in the world of time and causality, may not apply at the edge of time. We are trying to shine the lantern of human reason into a domain where its light may not reach. And yet, there is a remarkable harmony between the scientific and the mythological. Both seek to weave narrative into mystery, to make sense of beginnings by telling stories, whether in equations or in poetry. Both confront the paradox that the origin of time must itself lie outside of time. Both acknowledge that the question may never be fully resolved, yet remains irresistible. This harmony reveals something profound. The human impulse to seek origins is itself part of the story of time. The universe gave rise to creatures who wonder, who invent myths, who build theories, who peer into the darkness before beginnings. Our questions are not accidents, they are continuations of the cosmos's unfolding. The mystery of time is not only external, but internal, not only about the universe, but about ourselves. This is perhaps why the question of what came before the Big Bang captivates so deeply. It is not only about physics, but about meaning. To ask it is to ask about our place in the cosmos, about whether the universe is a singular story or one among many, about whether existence is contingent or necessary, fleeting or eternal. It is to confront the limits of knowledge and the vastness of ignorance, and to find wonder there. Science does not diminish this wonder, it deepens it. By exploring inflation, quantum gravity, multiverses, and cyclic cosmologies, we give new language to ancient questions. We transform myths into hypotheses, stories into models, poetry into mathematics. But the spirit is the same, to look into the abyss and dare to imagine what lies beyond. And as we do, we also confront the possibility that there may never be a final answer. The universe may be infinite in its mysteries, each revelation opening new questions. The search for what came before the Big Bang may never conclude, but in the searching, we enrich our understanding, expand our vision, and deepen our connection to the cosmos. For now, the singularity remains our horizon, the point where questions dissolve into paradox. But even if we cannot cross it, we can circle it, exploring its implications, its echoes, its reflections in myth, philosophy, and science. And in doing so, we may discover that the true significance of the question is not in the answer, but in the asking itself. If philosophy gives us the questions, observation gives us the hope of answers. For all our theories of time before the Big Bang, of cycles, multiverses, bounces, and timeless quantum states, what ultimately matters is whether we can test them, whether the cosmos itself carries scars or whispers of its prehistory. Science is not content with speculation, it demands evidence. And so, to search for what came before the beginning, we turn to the sky, to the relic light that has traveled across 13.8 billion years to reach us, and to the ripples in space-time that may yet carry messages from the dawn. The most direct window into the early universe is the cosmic microwave background, CMB. This faint radiation bathes the cosmos, the cooled remnant of the primordial fireball that once filled all space. Discovered by accident in 1965 by Arno Penzias and Robert Wilson, the CMB is often called the afterglow of creation. It was released just 380,000 years after the Big Bang, when the universe cooled enough for atoms to form, allowing light to travel freely. To peer into it is to look back nearly to the beginning. Satellites like COBE, WMAP, and Planck have mapped the CMB with exquisite precision, revealing tiny fluctuations in temperature, ripples that mark the seeds of galaxies. These maps are triumphs of science, turning faint static into a cosmic blueprint. But beyond their beauty lies the tantalizing possibility that they might carry traces of what happened before. If the universe passed through a bounce, or if it bears echoes of previous cycles, the CMB may contain subtle anomalies, deviations from the random patterns expected by standard cosmology. Some scientists, including Roger Penrose, have claimed to see such anomalies. concentric circles in the CMB that might be the signatures of black holes evaporating in a prior eon, according to his conformal cyclic cosmology. Others remain unconvinced, arguing that the patterns are artifacts of noise, statistical illusions conjured by chance. The debate continues, fierce and unresolved. Yet the mere possibility that the CMB could carry information from before the Big Bang electrifies the imagination. It transforms the question of before from metaphysics into testable science. Another avenue lies in gravitational waves, ripples in space-time predicted by Einstein and first detected in 2015 by the LIGO Observatory. These waves, produced by colliding black holes and neutron stars, are faint but real, carrying information about cataclysmic events across the cosmos. But beyond the astrophysical sources we can already detect, there may be a primordial background of gravitational waves, generated in the first instance of the universe. Unlike light, which cannot pass through the opaque plasma of the early universe, gravitational waves would have traveled freely from the very beginning. To detect them would be to hear the universe's first heartbeat. If we could measure these primordial waves, they might tell us whether inflation occurred, whether the universe bounced, whether cycles left imprints. Experiments are already underway. Detectors on Earth and plans for space-based observatories like LISA aim to open this new window. It is a long shot, requiring sensitivity beyond anything yet achieved, but the potential reward is staggering. In the hum of space-time itself, we might find the signature of a time before time. Closer to home, particle physics offers another route. The conditions of the early universe were so extreme that recreating them requires accelerators of immense power. The Large Hadron Collider has probed energies far below those of the first second, but still enough to discover the Higgs boson, the particle that gives mass to matter. In its discovery lies a clue. The Higgs field permeates space, shaping the properties of particles and forces. But is the Higgs unique? Could there be other fields, hidden, that drove inflation or sieved universes? If so, experiments might glimpse them, offering insight into the physics of the beginning. Even more speculative are searches for signatures of extra dimensions, predicted by string theory. If additional dimensions exist, curled up tightly, their effects might show up in particle collisions or subtle deviations in gravity at small scales. If found, they could confirm that our universe is part of a higher dimensional structure, lending credence to brain cosmology and the idea that the Big Bang was a collision in a larger space. Dark matter and dark energy, too, may hold keys to the mystery. These invisible components make up 95% of the universe, yet remain elusive. Dark matter binds galaxies together, while dark energy drives cosmic acceleration. If we can understand their nature, we may also understand the deeper framework of reality, the rules that govern the universe's birth. Perhaps dark energy is not a constant, but a field that evolves, hinting at transitions before the Big Bang. Perhaps dark matter is a remnant of particles formed in a prior era, fossil evidence of a cosmos older than our own. And yet, for all these efforts, the greatest challenge remains that the universe hides its earliest moments behind a veil. The Planck era, the first 10 to the minus 45 seconds, is beyond direct observation. No light, no signal, no wave may reach us from that time. We are left to infer, to model, to speculate. The dream of science is to pierce this veil, to turn speculation into observation. Whether through the CMB, gravitational waves, particle physics, or subtle cosmic anomalies, we search for cracks in the wall. But perhaps the wall itself is part of the lesson. Perhaps the origin of time is not something we can observe directly, but something we must approach obliquely through traces, echoes, shadows. Just as archaeologists reconstruct ancient cities from fragments, we reconstruct the birth of time from hints scattered across the cosmos. The task is humbling, but also exhilarating, for even in the limits of knowledge we find wonder. And here, philosophy and science converge again, for the question of what came before the Big Bang may never be fully answered. It may be that time, in its deepest essence, is beyond human comprehension. And yet, the act of searching changes us. Each new observation expands our vision, reminding us that we are part of a universe far larger, stranger, and more mysterious than we can know. But still, hope persists that the sky holds secrets yet to be revealed. The next generation of telescopes, detectors, and experiments may yet uncover evidence of a pre-bang reality. Perhaps in the polarization of the CMB, in the hum of gravitational waves, in the particles glimpsed in accelerators, we will find the first whispers of time's birth. And if we do, the impact will be profound, not only for physics, but for philosophy, for humanity's understanding of its place in the cosmos.
For now, we stand on the shore of an ocean of ignorance, casting our instruments into the deep, hoping to draw up fragments of a world beyond beginnings. Whether we succeed or not, the search itself is a triumph. It is the expression of our deepest nature, to wonder, to question, to seek. And in that seeking, we mirror the universe itself, unfolding, evolving, reaching toward the unknown. But there is one more frontier we must explore, the fate of Earth and of humanity in the grand story of time. For the cosmos may be infinite, timeless, and eternal, but we are not. Our world has its own beginning, its own end, its own arrow of time. To complete the story, we must turn from the cosmic scale to the planetary, from galaxies to the fragile blue sphere that is our home. From the silence of cosmic origins, we turn our gaze to Earth, a small, fragile world orbiting an ordinary star, yet cradling the only known consciousness capable of contemplating the beginning of time itself. For all the grandeur of galaxies and the violence of black holes, it is here, on this pale blue dot, that the question of what came before the Big Bang finds its most intimate relevance. Because no matter how timeless the universe may be, our planet and our species live by the ticking of a finite clock. Earth was born some 4.5 billion years ago, sculpted from the debris of earlier stars. Long before it cooled, long before oceans spread across its surface, the heavy elements of which it is made were forged in stellar furnaces and scattered in supernova explosions. Each atom of carbon in our bodies, each trace of iron in our blood is a relic of stellar death. We are the dust of stars condensed into life. And yet, the story of Earth is inseparable from the story of time itself. The arrow of time that began at the Big Bang drives the evolution of planets as surely as it drives the birth of galaxies. Earth orbits the Sun in a dance dictated by gravity, its days marked by rotation, its years by revolution. But beneath these rhythms, deeper currents flow, tectonic cycles that reshape continents, climate shifts that carve ecosystems, biological processes that build and extinguish species. Time is written in the layers of rock, in the rings of trees, in the fossil record of vanished lives. To study Earth is to study the passage of time made tangible. Humanity emerged only recently in this vast chronology, a flicker at the end of billions of years. Our ancestors gazed at the stars with wonder, telling stories to explain their movements. But only in the last few centuries have we begun to measure time with precision,
to align it with the physics of the cosmos. In pendulums, in quartz crystals, in the vibrations of cesium atoms, we have captured time's steady march. These inventions are not merely tools, they are reflections of our desire to anchor ourselves in the river of becoming. And yet, even as we measure time, we are bound by it. Civilizations rise and fall. Generations succeed one another. Lifespans unfold and end. Entropy advances everywhere, and Earth is no exception. Our planet, though seemingly eternal, is transient. Its oceans will one day boil away, its continents dissolve, its biosphere vanish. The clock of Earth is ticking, just as the clock of the universe ticks, though on scales we can scarcely comprehend. The most dramatic change awaiting Earth is tied to the life cycle of the Sun. Our star, now about halfway through its 10 billion-year lifespan, will one day swell into a red giant, expanding to engulf the inner planets. Before that catastrophic climax, increasing solar luminosity will slowly render Earth uninhabitable. Within 1 billion years, oceans may evaporate away, stripping away the conditions for life. Long before the Sun's fiery death, the cradle of humanity will be no more. It is a sobering thought that all of human history, from ancient civilizations to the digital age, unfolds in a brief window between Earth's fiery birth and its inevitable demise. We are caught between two abysses, the mystery of what came before the Big Bang and the certainty of what lies ahead for our world. In contemplating both, we find a strange symmetry. Time stretches endlessly backward into speculation and theory, and forward into destiny and loss. But within this window, life flourishes. It is here, in this fragile epoch, that intelligence arose, and with it, the power to ask cosmic questions. The atoms forged in stars became neurons, capable of wondering about the birth of time itself. This is the paradox of our existence. Tiny beings on a tiny planet daring to ask questions about infinity. It is as though the universe, through us, reflects on itself. And as we probe these mysteries, we also confront our own vulnerability. The fate of Earth is not only sealed by stellar evolution, but shaped by human action. Climate change, nuclear weapons, ecological collapse, these are threats that compress cosmic timescales into human lifetimes. In a sense, our mastery of knowledge has given us the power of creation and destruction. We are the first species capable of understanding the destiny of our planet, and the first capable of altering it. Time is not merely something that happens to us, it is something we can shape, for better or worse. Yet, the end of Earth need not mean the end of humanity. Our species has already begun to dream of leaving its cradle, of spreading into space, of outlasting the death of our planet. Colonies on Mars, voyages to distant stars, the building of artificial worlds, all are attempts to wrest control from time, to endure beyond the limits set by biology and planetary fate. In these dreams, we echo the cycles of the cosmos itself, rebirth following destruction, continuity beyond endings. But even if humanity endures, even if we spread across the stars, the question of time's origin remains, because survival is not the same as understanding. To live is one thing, to know why we live and how existence itself arose is another. Earth reminds us of both, the fragility of our condition and the grandeur of our curiosity. From its rocks and oceans, we learn of beginnings and endings. From its skies, we learn of cosmic scales. And from its people, we learn that meaning is not only found in survival, but in the pursuit of truth. The destiny of Earth is to vanish. The destiny of humanity is yet unwritten. But the destiny of the universe and the meaning of time itself remains the deepest mystery. What came before the Big Bang? Was there another universe, another cycle, another reality? Or was the birth of time itself the absolute beginning? These questions reverberate across every scale, from the fate of galaxies to the lifespan of our world. Perhaps in some distant future, long after Earth has perished, the answers will be known. Perhaps descendants of humanity, or of some other intelligence, will have deciphered the equations that describe the timeless state, will have glimpsed the structure of reality beyond beginnings. If so, the story of time will not end with Earth. It will continue, written across the stars, echoing through the ages. And so, in turning our gaze from the cosmos to Earth, we find that the story of time is not abstract. It is woven into our very existence. We are creatures of time, born in its flow, destined to perish within it, yet capable of reaching beyond it with thought. Earth is our stage, but the play is cosmic. Our lives, our civilizations, our species are but acts in a drama that began before we can know and will continue after we are gone. The Big Bang may have been the beginning of time as we know it, but it was not the end of mystery. The universe still hums with questions, and Earth for now is the one place where those questions are asked. To be alive here now is to be a participant in the greatest story ever told, the story of time itself. And as the sun sets over our world, as the stars blaze in the night sky, we feel both the weight of our finitude and the exhilaration of our inquiry. For though Earth is temporary, though all things must pass, the act of asking, the act of seeking, the act of imagining, these are timeless. They are the sparks by which a finite species touches the infinite.
The fate of Earth draws us into the broader fate of the cosmos. For as surely as planets perish and stars fade, so too does the universe itself evolve, under the relentless governance of time. The question is not only where we came from, but where everything is going. If the Big Bang was the dawn, then what awaits at the dusk? Cosmologists have long grappled with this question, proposing visions of the ultimate destiny of existence. The answers are not definitive, for they depend on forces still only partly understood: dark energy, dark matter, the curvature of space-time. But each scenario paints a portrait of endings on a scale that defies imagination, endings that stretch trillions of years beyond the brief lifetime of stars, beyond the lifespan of galaxies, into an abyss of ages that makes even the birth of Earth seem recent. One vision is the Big Freeze. In this future, the expansion of the universe continues indefinitely. Galaxies recede ever farther from one another, their light stretched until it fades into invisibility. Stars exhaust their fuel and wink out, leaving behind white dwarfs, neutron stars, and black holes. Over unimaginable eons, even these remnants grow cold and inert. The cosmos becomes a dark, diffused wasteland, punctuated by the occasional evaporation of black holes, their mass dissolving into the void as faint radiation. In this frozen eternity, time continues, but nothing happens. The universe does not end with a bang, but with an eternal whisper. Another possibility is the Big Crunch. If gravity ultimately overcomes the repulsive push of expansion, then one day the universe may reverse its course. Galaxies would halt in their flight and begin to fall back together, stars and planets colliding in catastrophic annihilation. Eventually, everything would collapse into a single searing point, an echo of the beginning. In such a vision, the end is indistinguishable from the start, and time itself might reset. What we call the Big Bang could only be one phase in an endless cycle of expansion and collapse, universes giving birth to universes in the rhythm of an eternal heartbeat. And then there is the most enigmatic future of all, the Big Rip. If dark energy grows stronger over time, accelerating expansion beyond all restraint, then the universe could be torn apart from within. Galaxies would first fly apart, then stars, then planets,
Eventually, even atoms themselves would be ripped into shreds of energy. In this terrifying vision, time carries all of existence not into stillness or rebirth, but into disintegration. Space and time themselves would unravel, leaving behind nothing. Each scenario forces us to confront the fragility of existence on scales so vast they challenge comprehension. Whether eternal freeze, crushing collapse, or universal rupture, all share one haunting truth. The cosmos, like Earth, is impermanent. Time itself may not end, but the structures it creates will fade, dissolve, or transform. And yet endings are not only destruction, they are transformations. The universe has been remaking itself from the start. Stars born from gas, planets from dust, life from chemicals, intelligence from biology. Perhaps the ultimate fate of the cosmos is not an end, but a passage into states of being we cannot yet imagine. After all, from the standpoint of physics, matter and energy are never destroyed, only rearranged. Even in the bleakest scenarios, something remains. The faint glow of black hole evaporation, the whispers of quantum fields, the fabric of space-time itself. For some thinkers, this raises the possibility that the end of one cosmos could seed the beginning of another. In certain models of eternal inflation, the death of one universe is but the birth pang of another, budding off from the quantum foam like bubbles in a boiling pot. If this is true, then what we call the Big Bang was not the beginning of time, but only one beginning among countless others, stretching into the infinite. We live inside a single bubble of reality, surrounded by an endless froth of other universes, each with its own laws of physics, its own version of time. But if this multiverse exists, then the question deepens. Is time universal or is it local? Does it stretch across the multiverse like a common thread, or is each bubble governed by its own clock, its own arrow? Perhaps time, as we experience it, is a parochial feature of our cosmos, irrelevant to others. Or perhaps it is a grand unifying principle, the ultimate constant binding all realities together. These are not idle speculations, they are attempts to wrestle with the greatest mystery of all, whether existence is singular or plural, finite or infinite. To bring these questions down to human scale is to ask, what do they mean for us? If the universe ends in a freeze, then time becomes an eternity without change. If it ends in a crunch, then time is cyclical, repeating forever. If it ends in a rip, then time itself dissolves into nothingness. In all cases, the destiny of the cosmos lies beyond human lifespans, beyond civilizations, beyond the span of stars. But the knowledge of these fates alters how we see ourselves, here and now. For though we cannot control the expansion of the universe, we can choose how we live within the sliver of time allotted to us. The grandeur of cosmic futures does not diminish human meaning, it deepens it. To know that the universe itself is mortal is to understand the value of every moment, every thought, every life. To know that time may stretch endlessly or collapse suddenly is to see our fragile existence in sharper relief. Against the backdrop of eternity, our lives may seem like sparks in the dark, but sparks are no less real for being brief. They are the light by which meaning is made, and perhaps, just perhaps, humanity is not powerless in the face of cosmic fate. Already we contemplate technologies that might extend life, preserve consciousness, even manipulate space-time. Already we imagine civilizations that could survive the death of stars, build habitats around black holes, harness energy from the quantum vacuum itself. These are not certainties, but possibilities, dreams in which intelligence becomes a force not only within the universe, but upon its very destiny. If time had a beginning before the Big Bang, then it may have no end. If time is an emergent property of the cosmos, then perhaps it can be shaped, altered, redirected by advanced beings. These ideas border on the mythic, yet they are grounded in the same human impulse that once built fire, crossed oceans, split atoms. We dream because we live within time, and dreaming is a way of reaching beyond its limits. The universe will end one way or another, but what matters for us is what we do with the time between beginning and end. This is the true message of cosmic destiny, that the story of time is not only written in galaxies and equations, but in choices, in actions, in the fleeting yet profound presence of consciousness. We are children of the stars, yet we are also authors of meaning. And so, as the universe stretches forward into trillions of years, we return to the mystery of its origin. What lies before the Big Bang? What lies after the end? These are not just questions for science, but for existence itself. For to know the fate of the cosmos is to glimpse the framework of being. To ask where time began is to ask why there is something rather than nothing. The story continues, as it must, into the farthest reaches of possibility. As we near the end of our journey, the question of time's beginning before the Big Bang takes on an almost paradoxical weight. It is not merely about physics, equations, or cosmological models. It is about the most fundamental mystery of existence itself. To ask what came before the beginning is to confront the limits of thought, the edge where science, philosophy, and imagination collide. Time, in our experience, is so deeply woven into reality that to picture its absence is almost impossible. The mind slips, recoils, stumbles. Yet the greatest scientists have dared to press into that silence. Stephen Hawking once remarked that asking what came before the Big Bang was like asking what lies north of the North Pole. The point was not to dismiss the question, but to show how time itself may have begun at that moment, making before meaningless. But even he acknowledged that deeper structures, quantum gravity perhaps, a multiverse, might exist beyond our limited understanding, where before regains meaning in forms we cannot yet fathom. In those deeper structures lies the heart of human wonder. If the Big Bang was the birth of time, then all of history, from galaxies to civilizations, rests upon a single event. If time predates it, then the Bang was not a birth, but a transition, a flare in an ongoing drama whose first act lies hidden. Either way, the implication is staggering. Time, whether finite or eternal, is the canvas upon which all reality is painted. Scientists attempt to map that canvas using mathematics, the most precise language we possess. Equations like Einstein's field equations or the probabilistic rules of quantum mechanics act as lenses through which the unseeable becomes glimpsed. But mathematics is not the universe itself, it is our translation. When cosmologists debate loop quantum cosmology, string theory, or eternal inflation, they are offering not answers but interpretations, each striving to pierce the veil of what lies beyond our reach. Each carries beauty, elegance, and daring, but also incompleteness. For every model solved, new questions bloom. This is not a failure, it is the essence of discovery. Consider history. Once humans believed Earth was the center of the universe. Then we learned it orbits the sun. Then that the sun is but one star in the galaxy one among billions. Each expansion of perspective felt disorienting, even frightening. Yet with each came a new sense of awe, a richer sense of connection to the whole. So too with time. Whether it began at the Bang or stretches beyond it into infinite cycles, each possibility deepens the mystery and expands the horizon of thought. And so we arrive at the philosophical frontier. What does it mean for beings like us, brief and fragile, to live inside such immensity? If time is eternal, then our lives are but moments, passing like dust in a cosmic wind. If time had a beginning, then everything, including our thoughts right now, are part of a finite, perhaps singular, story. Both visions are humbling. Both remind us that meaning is not given by scale, but by experience. For in one sense, the universe does not know it exists. Galaxies spin, stars collapse, black holes consume. But none of these ponder their own being. Only conscious life, as far as we know, can reflect on time, on beginnings and endings. That makes our awareness rare, perhaps unique. To wonder where time began before the Big Bang is not simply curiosity, it is the expression of the cosmos awakening to itself through us. The existential implications are profound. If time has no beginning, if reality stretches infinitely backward and forward, then we are threads in an eternal tapestry, our lives woven into patterns too vast to see. If time began, then everything, including our thoughts right now, are part of a finite, perhaps singular, story. Both visions are humbling. Both remind us that meaning is not given by scale, but by experience. But in one sense, the universe does not know it exists. Galaxies spin, stars collapse, black holes consume. But none of these ponder their own being. Only conscious life, as far as we know, can reflect on time, on beginnings and endings. That makes our awareness rare, perhaps unique. To wonder where time began before the Big Bang is not simply curiosity, it is the expression of the cosmos awakening to itself through us. The existential implications are profound. If time has no beginning, if reality stretches infinitely backward and forward, then we are threads in an eternal tapestry, our lives woven into patterns too vast to see. If time began, then we live in a story with a first page, a story whose existence itself is miraculous. In either case, to exist at all is an extraordinary improbability. Against the silence of non-being, we are here, aware, asking. That alone is a kind of miracle. But human beings are not content with awe. We are restless, driven to act. And so these questions about time's origin spill over into our future. For if time is endless, then might we endure beyond Earth, beyond the lifespan of the Sun, perhaps even beyond the fate of this universe? Could intelligence learn to ride the currents of cosmology itself? To survive heat death or escape into other universes? Some physicists propose that advanced civilizations might, in principle, manipulate space-time on scales we cannot yet imagine, opening wormholes, creating pocket universes, even seeding new beginnings. If so, then time's story might not be only one of blind physics, but of participation, of agency. It is here that science and myth converge. In myth, gods create worlds, shape destinies, bring light out of chaos. In science, we speak not of gods, but of laws, particles, energies. Yet the idea that intelligence could one day help shape the cosmos is not far from mythic creation. We stand at the edge of possibilities so immense they blur into visions that feel spiritual. To imagine time before the Big Bang is to imagine creation itself, not just once, but always. And through it all, Earth remains our cradle. This blue planet, circling a star in the arm of a spiral galaxy, is where time became personal, where chemistry became consciousness. Earth is fragile, its atmosphere thin, its biosphere delicate. Compared to cosmic timescales, our world is transient. One day the sun will expand and consume it. Long before then, humanity must choose whether to remain bound here or to carry the spark of awareness outward. That decision will shape whether our story ends with Earth or continues among the stars. Time may have begun before the Big Bang, or it may not. We may one day know, or the truth may forever remain veiled. But perhaps the greater truth is this: the very act of asking binds us to the universe. We are not separate from time, nor from the cosmos. We are of it, expressions of its unfolding. To seek the beginning of time is to seek our own beginning. To wonder about the end is to wonder about ourselves.
And so the story circles back, not to an answer, but to a recognition that we exist in mystery, that to be alive in a universe at all, finite or infinite, beginning or eternal, is an unspeakable gift. Time flows, carrying us all, from Big Bang to black hole, from atom to thought, and in that flow, we awaken. The journey has led us across billions of years, through collapsing stars and expanding universes, into realms where mathematics strains to keep pace with reality, and into questions where physics and philosophy merge. We have stood at the precipice of time itself, asking what it means for there to have been a before the Big Bang. And now, as we bring the threads together, we return to the most intimate horizon of all, ourselves, here, in this fragile moment of existence. The mystery of time's beginning is not only about physics, it is about meaning. If time arose with the Big Bang, then we are witnesses in a story with a true genesis, a creation whose very existence is miraculous. If time stretches infinitely into the past, then we are fragments of an eternal river, our lives moments of awareness in a current without origin or end. Both visions are breathtaking, both carry weight, and both, in their way, remind us how precious each instant of our brief lives truly is. For we are creatures bound to time. Each heartbeat, each sunrise, each memory, these are threads in our own finite span. We cannot step outside the flow, cannot stop its current, cannot glimpse the landscape from above. We live within the unfolding. And that makes the question of where time began not merely a curiosity, but a reflection of our own mortality. When we ask what came before the Big Bang, we are, in a sense, asking about ourselves. Where do we come from? And what awaits us beyond our horizon? Science, though, is not satisfied with wonder alone. It reaches forward, ever probing, ever testing. The telescopes we launch, the particle accelerators we build, the detectors buried deep underground or floated in space, these are our eyes and ears stretched to the limits of the possible. They are attempts to listen for the faintest whispers of creation, the faintest ripples of time's origin. The discovery of cosmic microwave background radiation was one such whisper, a fossil glow from the universe's infancy. Gravitational waves may one day reveal even earlier tremors, perhaps direct echoes of the moment of inflation. And quantum experiments may point to hidden geometries of space-time, blueprints of realities beyond our own. Yet, even as technology advances, there remains the possibility that some truths will forever elude us. The earliest moments of time may be veiled by horizons we cannot cross, laws we cannot overturn, or paradoxes we cannot resolve. To some, this is frustration. To others, it is wonder that the universe retains its secrets, that mystery is woven into its very structure. In this sense, the question of time before the Big Bang may be eternal not just in physics, but in the human imagination. But what then do we do with this mystery? One answer is to recognize its power to shape how we see our place in the cosmos. Whether time had a beginning or not, whether there are countless universes or only one, we are here, now, conscious of it. That consciousness is not trivial. It is the only lens we know through which the universe can reflect upon itself. In a universe vast and cold, where stars burn and fade indifferent to meaning, the spark of awareness on a tiny planet is extraordinary. It is not the size of our place that matters, but the fact that it exists at all. This realization leads us forward to the fate of Earth. Our planet will not endure forever.
In a few billion years, the sun will expand, swallowing its inner worlds. Long before that, human activity may decide the trajectory of life here, through care or through neglect. The cosmos, in its grandeur, may continue for trillions of years, but Earth is fleeting. To grasp the immensity of time is to feel the urgency of the present. For in the scale of the universe, now is all we have. Yet there is also hope in that urgency. Humanity is young, perhaps only at the dawn of its story. The same curiosity that drives us to ask about time's beginning may one day carry us beyond Earth, into the solar system, and perhaps beyond. Our understanding of cosmology is not only about knowledge, it may also be about survival. If time stretches endlessly ahead, then the challenge is to learn how to endure within it, to adapt, to explore, to carry the fragile flame of awareness into the great dark. And if time began, if it has a limit, then the challenge is different: to make meaning within finitude, to treasure the story as one whole, however brief. In both cases, the lesson is the same. Our lives matter, not in spite of their brevity, but because of it. To exist at all, against the silence of non-being, is wonder enough. Perhaps that is the true answer to the question of how time could have begun before the Big Bang. Perhaps the answer is not in equations or theories alone, but in our response to the mystery. To look up at the night sky and feel awe, to recognize ourselves as part of a universe that is both knowable and unknowable, familiar and alien. To live not in despair of our smallness, but in celebration of it. Time is vast. It may be eternal. It may have been born in a single instant of unimaginable energy. We may never know its full story, but what we do know is that it flows through us, shapes us, carries us. Every second of our lives is a ripple in the ocean of time. Every choice we make, every thought we hold, is part of the unfolding of the universe itself. And so, in the end, the story returns not to the Big Bang, nor to what came before, but to us, here, in this fragile moment on Earth. For though time may have no beginning, and though it may stretch beyond all horizons, what matters most is how we live within it. We are stardust asking about eternity. We are fleeting beings daring to wonder about infinity. We are, in a very real sense, the universe dreaming of its own beginning. And perhaps that is enough.